Good morning, one and all. Indeed, it is a great pleasure to introduce today's distinguished speaker to all of you. Though I'm sure most of you already know about Professor Yogendra Singh from IIT Roorkee. Professor Yogendra Singh is currently the Railway Bridge Chair Professor at the Department of Earthquake Engineering at Indian Institute of Technology, IIT Roorkee. He had completed his Bachelor's of Engineering in Civil Engineering from IIT Roorkee, which then it was called University of Roorkee. Subsequently, he pursued his MTech master's degree and PhD degree from Indian Institute of Technology, IIT Delhi. He has received number of awards and honors during his distinguished and illustrious career in academia. His research interests are broadly in the areas of performance-based seismic design of buildings and bridges, seismic risk estimation, seismic soil structure interaction, and earthquake engineering in hill regions. He is serving as an expert member on several national committees constituted by various government organizations such as NDMA, Ministry of Home Affairs, CPWD, NIDM, to name a few. He is also an active member of the Code Committee for Indian Standard 1893-1893, which all of us are familiar, on criteria for earthquake resistant design of structures. He has supervised more than 15 PhD theses, more than 50 MTech dissertations, and number of sponsored research and consultancy projects were completed under his headship. He published more than 200 publications, including journals, books, monographs, reports, conferences, and special publications. And he has organized 43 short-term training programs on various topics related to earthquake-resistant design of structures. He had served as head of the department at Earthquake Engineering Department in IIT Roorkee. Now, under the ISET webinar series today, he will be presenting on the performance-based seismic design of structures, and we are all eager to hear from Professor Singh. So I request Professor Singh to please deliver his webinar. Professor Singh, please.
Thank you, Professor Matsagar, for the introduction. Good morning, all who have joined this morning. So thank you very much for joining, and I'm also thankful to ISET for giving this opportunity to be able to talk to you. So as the topic has been already communicated to you, today we are talking about performance-based design, performance-based seismic design of structures. So I think now you can see my screen.
Yeah. Yes, sir.
Yeah.
Yes, sir.
Yeah. Thank you. So, okay. So, what's this performance-based seismic design? I was looking at the list of the participants who have registered for this webinar, and I could see that there is a mix of the background. So, from senior teachers to students, different background people are there. So I will try to take a middle path where I will touch on some fundamentals, and at the same time I will be talking about performance-based design concepts as well. So those who find some of these concepts trivial and well known, please bear with me, because I have to cater to those students also who have who may not have much background in earthquake resistant design. So you may be knowing that earthquake resistant design or the subject itself is relatively new compared to structural design. So structural design is there for long, but earthquake resistant design developed post 1950 era, and performance-based design developed even more recently. Most of the development has taken place in this century, and some initial works started in 1990s. So late 1990s, so 20 to 30 years development is there. And the courts world over are in the process of incorporating performance-based design in their guidelines. Our code, Indian code, is also, committee is working on developing a separate code or a part of ISET 93 on performance-based design. So that is on. So this is the right time that we should start learning performance-based design and using it. In many companies now, the performance-based design is being used in design offices as well. So this is now becoming important to the practicing sorry, structural engineers as well. So this before coming to this performance-based design, let me give you a small overview of what is our current practice of design. So currently we are designing using a response reduction factor. So you may be knowing that earthquake is a very rare phenomenon, but it causes very high forces. When we are talking about wind or flood, we talk about 50 years or 100 years return period. But when we are talking about earthquake, we talk about something like 2,500 years return period. So that shows that it is a rare phenomenon. So we consider much less probability of occurrence as compared to other actions for which we are designing our structures. But at the same time, the consequences of earthquake are much far-reached. So we can have a devastating effect. We are going through one disaster at the moment, which is a natural phenomena and related to medical science, and it has so much impact on the economy. So earthquake does not have that type of impact, but it can have a similar impact on a region because it will affect a region around the epicenter. Some up to 200 kilometers around the epicenter will be subjected to huge losses. And those losses do not only have the social impact, these also have economic impacts. So we when we design for earthquake, we never design for the actual force. So I will explain what do I mean by actual force. So when we are designing for gravity or for wind, we are always having a factor of safety. And in case of earthquake, there is no factor of safety. In fact, what capacity we are designing for is less than the actual force which will come on an elastic structure. So for example, in this figure, you see this blue curve at the top. This is representing the demand, which is nothing but response spectrum. So response spectrum is, okay, I will approve that. So the response spectrum is representing the demand which we are expecting on our structure. Then what we do, we reduce it by a response reduction factor R, which you know varies from 1.5 in case of masonry to 5 in case of especially designed or especially detailed moment resisting frames and steel frames. So we divide by, let us say, about 5, and then we use some factors of safety. This use of partial factors of safety on load as well as on material gives us a false impression that we are having a factor of safety in case of earthquake. But actually, there is no net factor of safety. Because of these factors of safety, the strength of the structure increases to almost double. So the actual strength of the structure is given by this light blue curve here. So we estimate the earthquake demand, reduce it by response reduction factor, then apply certain factors of safety, and we design it like this. So if you recall the formula which we use for calculation of base shear, we do ZY2 IYR into SAYG. So this 2R is the reduction. So we reduce it roughly 10 times, then increase it to double because of the partial factors of safety. So we end up designing our structures only for 1/5 of the force which is expected on an elastic structure. So what happens when the structure is subjected to a force which is approximately 5 times? So it yields under that force, and we design our structures in such a way that those should yield but should not collapse. And because of the yielding, there is inelastic energy dissipation, hysteresis, and due to that hysteresis, the energy due to earthquake gets dissipated. So we have to design our structures in such a way that the structure should, yeah, any comment? So the structure should be designed in such a way that it should be able to dissipate the energy which is being imparted by the earthquake. The structure should be able to dissipate energy at the same rate or at a higher rate. So if the structure is able to dissipate energy at same or higher rate, it will survive the earthquake. And that is our current philosophy of design. So this response reduction factor, this is the key parameter in our design. And our code provides a list of these response reduction factor. You might have wondered from this response reduction factor has come. This response reduction factor represents the energy dissipation capacity, inelastic energy dissipation capacity of the structure. But it is not based on any experimental or analytical studies. It is based on our experience during past earthquakes. So code committees have decided these response reduction factors. And that is the weakness of the current design method, because these response reduction factors are based upon judgment. And this judgment is based upon the past earthquake experience. And that's why in our code, or in all the codes of the world, there are a lot of do's and don'ts. So these response reduction factors are applicable to only certain types of buildings, which are regular and symmetric. If the building is irregular and symmetric, then this judgment in the form of R may not be valid. And some of our designers are not happy with that, because these restrictions sort of restrict the creativity of the designer. So he can do only with certain types of buildings which are regular and symmetric. So if somebody wants to design an irregular and asymmetric building, it's not help. It is not. Another question is that suppose I have designed my structure with this current design philosophy based on response reduction factor. So what I am expecting during earthquake from my structure, how it is going to behave. The code does not provide a precise answer to that. If you look at the forward which was there in 1893 version, so that read like this, that the structure, when we are designing using as per that standard, then it may suffer damage during earthquake. And it is intended. The code did not have any framework for that, but the intention of the code was that as far as possible, in case of earthquakes of small magnitude, the structure will be able to respond without structural damage. And in case of moderate intensities earthquake, it will respond without, in case of small earthquakes, it will respond without any damage. In case of moderate earthquakes, it will have small structural damage, but in case of heavy intensities, it should not collapse. So ensuring no collapse was the intention of the code, but there was no framework for that. Even that was not possible to ensure. So in the latest revision, 2016, that has been changed. All those terms have been taken away. And the only statement given there is that structures designed as per this standard are expected to sustain damage during strong earthquakes. So it means only damage. But what will be the level of damage? Even that, whether it will be able to survive the earthquake, will it not collapse during the earthquake? Even that is also taken away. That has been taken away from the forward. So the code is not even taking that guarantee that it will not collapse. So this is a big limitation of our design. If we tell this to our client who has come to us for design, and we tell him that we will do as per the current practice, and we do not know whether the structure will be able to survive the earthquake or not. So that's not a good scenario. And moreover, we have several other structures which are important after earthquake. So those structures we want to remain operational. That cannot be ensured with the current design practice. And that's why we have to look for a more advanced design practice, which is available in the form of performance-based design. So in which cases we may need to perform performance-based design. One is when we have to quantify the performance of the designed structures. So we may design our structures using current code, but in that case, we do not have any idea how that structure is going to perform during a future earthquake. So if I want to have a reliable estimate of the performance, I have to go for performance-based design. Then for design of important buildings, which have either post-earthquake importance or have a hazardous consequence, those buildings need to be designed for better performance. So such a damage where the building is just at the verge of collapse, the collapse is somehow avoided. That type of design performance is not acceptable for these buildings. So there we have to go for performance-based design. Then there are many buildings which are code exceeding buildings. So these code exceeding buildings are either due to their height, where the current code is not applicable, or due to their irregular and abnormal configuration. So if there is any abnormality, irregularity in the structure, then also performance-based design is the only option available with us. Then there are many new and emerging structural systems coming. You may be aware that BMTPC has also advocated some new construction techniques, but our design codes are not available for those. If you see IS 1893, response reduction factors are available for certain classes of building. And if your building does not come in those classes, you cannot use the code because response reduction factor for that class is not known. So there it becomes essential to perform performance-based design. And when we are having buildings with response control devices, either in form of base isolation or dampers, then it is preferable because generally we design these buildings for better performance objectives. So in that case, we will like to perform the design using performance-based design. Although for these buildings, the conventional methods based on simplified analysis are also available. So if I have to differentiate the performance-based design with current design philosophy, then the main difference is that in case of performance-based design, we are designing for a set of performance objectives. So we define our performance objectives. Those performance objectives are in terms of performance levels corresponding to certain hazard levels. So two terms are important here: hazard level and performance level. I will explain what do we mean by that. And when we compare it with the conventional design, in conventional design we are applying limits on member forces. So as you know, we calculate a demand and we calculate a capacity, and then we ensure that the capacity is higher than the demand. But in case of earthquake, that demand is not realistic. That demand is reduced by a response reduction factor. So as I said, that in case of performance-based design, we need a set of performance objectives which are based on hazard level and performance level. So the performance level is an estimation of the expected damage. And when we are talking about damage, we consider both structural as well as non-structural damage. And this quantification, this limit on the damage is based on two aspects. One is the threat to the life of the occupants. So we want that the occupants of the building should be safe. And another is post-earthquake serviceability. So if there are some structures which we want to remain serviceable during after earthquake, then our damage should be limited accordingly. And these are quantified in terms of inelastic member deformations, because how to quantify damage? So damage in individual members can be quantified in terms of inelastic deformation. When the inelastic deformation reaches its ultimate value, then it will collapse. Before that, there will be varying degree of damage. Then it is also expressed in terms of inter-story drift. So inter-story drift ratio is a very important parameter. Usually we use to control the damage or the performance of the because the building may be housing some activities in which acceleration is important. So we have to restrict the floor acceleration also. So any or combination of these three parameters we use to define our performance objectives. Then these are some references which are available. The most important reference is this ASC 4117. And if you read the title, it talks about seismic evaluation and retrofitting. So this performance-based design was initially developed for evaluation and retrofitting of the building. That's why a code on retrofitting covers performance-based design. For design of new buildings, still most of the code of the world are depending more on the conventional method. Why? Because when we are designing a new building, we will like that the building performance should be better. So irregularity of configuration, continuity, ductility, we will like to ensure. So a new structure, when we are designing it, we should not introduce these aspects which compromise the behavior of the structure. But when we are evaluating an existing structure that may be constructed in any way, these features may or may not be there. So that's why the field of evaluation is much more wider, and these developments took place in the field of evaluation of performance of existing structures. But these are applicable to design of new buildings as well, and we can use these principles for design of new buildings. Then a separate development took place in the form of displacement-based design. This performance-based design is essentially displacement-based design. So our conventional design is force-based design, but in performance-based design, we use displacement as the design criteria. And the reason for that is that the displacement is a better indicator of damage. So the damage in any member or a structure can be represented better in terms of its displacement, especially the plastic displacement, inelastic displacement. The forces are not giving us that good idea of the damage. That's why another model code has been developed in Europe, and this is the front page of that code. And this our Federation for Tall Buildings that has also developed this model code 2010. So these are the three documents which are available, and you will find that the most elaborate is this ASC 41. So most of the things which I am presenting are available in ASC 41. Now this method, what we are actually doing, this performance-based design is based upon the realistic estimation of the ductility capacity of the structure, because the ductility capacity will decide how much energy our structure can dissipate. So we have taken this into account in our conventional design using response reduction factors. But here we are trying to estimate this value for a specific building, and it requires nonlinear analysis. And that's the main handicap in application of performance-based design in design offices, because it requires nonlinear analysis. And most of our engineers are not trained in nonlinear analysis. So nonlinear analysis is an essential part of performance-based design. So I will talk a little bit about nonlinear analysis also. And what is shown here, this brown curve, this is the capacity of the structure. And that the blue curve, as in the previous slide, it is the demand. So we have to determine an intersection of the demand and capacity in such a way that at that displacement, the energy dissipation, which is causing reduction in the demand, and the capacity curve, those intersect. This displacement at which this intersection is occurring, this we call performance point. And we check this performance point for the acceptance for our building, that whether it is satisfying the targeted performance level or not. If it is not satisfying the targeted performance level, we have to change our structure. So we have to iteratively change its strength and ductility in such a way that we get this performance point in the desired range. So it should be able to satisfy that performance levels which we have targeted in our design. So first I will talk a little bit about hazard. So we have to quantify the hazard, And the hazard is quantified in terms of its probability of accidents and the return period. Like we have return periods for floods and wind, we have return periods for earthquake. And as I said, that the maximum return period which we usually consider is 2,475, and roughly we say 2,500 years. This earthquake is also called maximum considered earthquake. Usually this earthquake we consider in our design. Except some hazardous structures like nuclear power stations, there are different periods, but for buildings and bridges, this is the reference hazard which we use. And it has a corresponding 2% probability of accidents in 50 years. So 50 years, usually that is our design period of the structures. So it has 2% probability of being exceeded in the design life. Then another earthquake which we are mostly using is this DBE, design basis earthquake. And it has 10% probability of occurrence in 50 years. So why this DBE, design basis earthquake, we call it design. Usually the expectation from our structures is that those will not collapse under MCE, maximum considered earthquake. But we design those structures using DBE. And it is understood that when we design our structures for DBE, and remember at DBE also when we are designing using a response reduction factor. So we design roughly to 20% of DBE. And then we are assuming, or the code gives us this assurance that the structure will not collapse under this MC. Then sometimes another important level of earthquake we use, which we call serviceability earthquakes. So this is used in the design of bridges. So if you have seen design of bridges for railways, they have a serviceability earthquake clause also. And that has a return period of 72 years. And it has 50% probability of occurrence in 50 years. So 50-50 chances of occurring in 50 years. So it is expected that this earthquake will occur more or less once in the lifespan of every bridge or every structure, which is being designed for 50 years. So under that earthquake, our structure should remain serviceable. So these are the limits. But other than these, also several limits have been used in literature. For example, 50% in 30 years, then 5% in 50 years, roughly 1,000 years return period. Those are also used. These limits are as per SC 41, which are prevalent in America. And in Europe, from this DDVD, you see, there are similar levels of earthquakes, 50% in 50 years. They also have a 20% in 50 years, 4% in 50 years. So it's up to us, depending on our requirement, whatever we want to target, we can decide a level of earthquake. But that is to be decided in terms of probability of occurrence in certain years, generally the design life of the structure, or in terms of a return period. So what we have in our code, there is a response spectrum and there are zone factors. So what are those zone factors representing? Those zone factors are representing the value of PGA. Now there is a question corresponding to which return period in our code. So some people think there is a misconception that JAD is for MCE, for 2,500 years return period. So let me tell you that currently our code is not based on probabilistic seismic hazard assessment, where the probability of accidents are obtained. It is based on deterministic seismic hazard assessment. And it shows the mean value of the deterministic seismic hazard. And if we multiply that 1.5, then it is considered to be equivalent to MCE. So if you have to get MCE earthquake, because in performance-based design, you will be requiring the definition of DB and MC. And currently our code is giving JAD and a spectral shape, which we multiply, then it becomes response spectrum. So if you multiply that JAD into 1.5, you will get MC. And when you divide by 2, you will get DBE. So MC is 1.5 times JAD, DBE is 0.75 times JAD, and SE is roughly 1 upon 1.5 of DBE. So that becomes JAD by 2. So ZY2 is actually serviceability earthquake, and 0.75 Z or 1.5 Z divided by 2, that becomes DVE, and 1.5 Z becomes MCE. That's why our code uses a load factor of 1.5 on earthquake. If you see other codes of the world, which are based upon probabilistic seismic hazard, so there the definition of MC or DVE is given directly. And in that case, the load factor for earthquake is 1. In our code, some of our engineers, when they compare it with our code with the other codes of the world, they think that our code is more conservative because we are applying a factor of safety of 1.5, but that is not true. So because the estimated values of Z which are given in our code, those are on lower side, being based on deterministic seismic hazard assessment mean values. We have to multiply those 1.5 to correct that. So that 1.5 is not really a partial factor of safety. It is a correction factor, converting the Z value to MC. Okay. Then the next issue is after hazard level, we have to define performance levels and performance objectives. So again, this table I have taken from SC41. Here you see there are structural performance level and there are non-structural performance level. So structural performance levels are numbered 1, 2, 3, 4, 5. Most important are this 1, 3, and 5. So this 1 is immediate occupancy. That means the damage is limited to an extent that the structure can be okay, and if you have some slot for question answer. So I will try to answer all your questions. We can even continue informally after the formal session is over. I will be available. So we can discuss that, but please keep your microphone muted. Otherwise, you will not be able to hear. So we have one performance level which we will like to target for important structures, let us say hospitals. This is immediate occupancy. Means such buildings will be having limited damage. Yielding will occur. Some energy dissipation will be there, but that inelastic displacement will be limited to an extent that the building will be usable immediately after the earthquake. Then another performance level which is important is this life safety. So life safety, as the name itself suggests, that there will be damage, there will be some falling debris, but the size of that debris will be limited to an extent that it may cause some minor injuries to the occupants, but there should not be any fatality. Then most of our codes currently depend on this collapse prevention. So where we ensure that the building will be damaged so badly that it will be at verge of collapse, but it will not collapse, because when a building is collapsing, there will be huge loss of life. A large fraction of the occupants in the building will die when the building is collapsing. So we want to avoid that. And if the building is having collapse prevention, then you should keep in mind that there will be injuries, and some of the injuries may be fatal also. So there is a possibility that 1 or 2 occupants may have a very severe injury which may cause death. But we do not want collapse. So collapse prevention only ensures that there should not be a large, huge loss of life. A large fraction of the occupant should not die. That is what we are intending. You may be frightened by this scenario that the building which you are designing as per code, you are designing in such a way that some fraction of the occupants will die if that MC earthquake is occurring. But keep in mind that it is a very, very rare phenomena, and the forces are very large, 10 times of that what we are designing for. So we take advantage of this rarity of the phenomena, and we design for lower forces. But there is a possibility, there is a probability of occurrence of this earthquake also. So at least we should target in our structure life safety, that the injuries are limited to that extent that nobody is fatally injured. And then in case of some structures, we have to go for immediate occupancy. Similarly, we have non-structural performance levels also, which are represented by alphabets A, B, C, D. So again, we have operational performance level where all the non-structural components will be secured so that those are functional. In case of a hospital, not only the building should be safe after earthquake, the non-structural components, equipment, services, pipelines, those should also be operational. So a combination of these two, that gives us the best performance level which we expect from a building, that it will be operational. Its structure will be intact, and its all services and equipment will also be working. So that is our best targeted performance level. Then we have a position retention. In position retention, we will ensure that all the major equipment are not falling from their position, because when those are falling, those will cause injury. And then life safety, where some equipment may be falling, but there is no chances of very severe injury, which may lead to death. And then lastly, we have not considered. So minimum we will like from any structure is this 5D, where the structure we will like to have no collapse, and the non-structural components we can ignore. So most of our common residential buildings are designed with this performance level. But as you can see here, all the combinations are possible. You can have some combination of structural performance, some combination of non-structural performance, and you can target any of these combinations. And some commonly used combinations are these three, which are shown here: life safety, immediate occupancy, and operational. And minimum is this 5D. So that's how, based upon this matrix, we decide our target performance levels. And then we have to ensure these performance levels through our design. And that will involve nonlinear analysis. And I will give you a little idea about nonlinear behavior of structures and how we can model those using our software which are available. So the the nonlinearity in the structure comes from the material. So whatever material we are using, that material itself has a nonlinear behavior. That's why we have nonlinear behavior in our structure. So every structure yields, every material yields. It may be bad for a designer, because the designer has to learn nonlinear analysis, but it is good for the structure because of this nonlinearity only. Because of the inelasticity, the structure is dissipating energy. So this inelasticity of materials is a desirable property, and this is quantified by a factor what we call ductility factor, and this ductility factor is the ratio of ultimate strain to the yield strain. So that ratio is important, and we want that this ductility should be as high in any material as possible. Larger the ductility, more energy the material will be able to dissipate. And most of our structures are made of either concrete or steel, or when we are talking about concrete, it is reinforced concrete. So it has concrete as well as steel. Now here you see this curve, this is smaller one. This is for unconfined concrete. So we know in unconfined concrete, the peak strain reaches around 0.002, and the ultimate strain is of the order of 0.004. So in our code, it is taken as 0.0035. In some cases, it may go up to 0.0045. So 0.0035 to 0.0045, that is the range. So if you calculate ductility of this, so this peak is not yield. Okay, yield occurs somewhere before that. So roughly we can take the yield strain, the notional yield strain in case of concrete as 0.0015. And if I take the ultimate strain as 0.004, I get something like 2.5. That is the ductility ratio in case of concrete. But that is a very small ductility for a material. Compare it with steel. In case of steel, the ultimate strain is of the order of 25%, 0.25, and yield strain is of the order of 0.002. So if you take the ratio of ultimate to yield there, it comes out to be 125. So there the yield ratio is 125. So compare 125 with this 2.5. So you can see that the ductility capacity of concrete is very, very low. We call it brittle material. Okay. But it is interesting that when we confine the concrete, if I somehow provide a lateral restraint to concrete, it can be in many forms, but commonly used in our design is through the stirrups. So if I properly confine it using the stirrups, then its strength and ductility increases. So what you see, this upper curve, this is the stress strain curve of confined concrete. So in that case, the strength as well as ductility increases. But still, this is much less than that of steel. Maximum we can go something like 3%, 2% to 3%. Usually we limit it up to 2%. So compared to steel, which is having 25% ultimate strain, this is also much less, but it is much larger than unconfined concrete. So the first thing which we have to do for earthquake resistance in our RCC structures is that we have to properly confine the concrete. Whether we are doing performance-based design or we are doing conventional design, there is no substitute for that. So we cannot think that performance-based design will change the material. The material will remain same, and we have to properly utilize our material. So this is the behavior of concrete. The different confining arrangements, those are compared here. So we can see the best confinement we can get is this C type of confinement. So confinement depends upon how many longitudinal bars we have on the perimeter which are restrained against outward movement. So we can see that here the maximum number of bars along the perimeter which are restrained by this arrangement of lateral or transverse reinforcement. So this is giving us the better reinforcement, confinement. So stress strain curve is more or less flat, and the worst we are getting in case of A. Then when we compare different types of steel, we have Fe250, mild steel, then we have high strength steels, then we have steel for pre-tensioning, pre-stressing, and we have strings which we use in cable stayed bridges. So the strength goes on increasing, but you can see at the same time the ductility goes on reducing. That's why the detailing code IS 13920 has a restriction over the strength of steel, because if you are using very high strength steel, you are losing the ductility. And in case of earthquake, strength and ductility both are important. In fact, ductility is more important than strength. As I said, that we are designing only for 20% of the forces. So 20% we depend on strength and 80% we depend on ductility. So ductility is even more important. So we will not like to compromise on ductility. So it's very important that whatever steel you are using, either in conventional design or performance-based design, that steel should have satisfactory level of ductility. And that is specified in the code that it should have at least 14.5% elongation. So we take our material, steel and concrete, then put that in a section. You all know how to analyze a section that we learn in our RCC design course. By assuming plane sections remaining plane, we get a strain diagram, and then we can get the corresponding stress variation. Mostly concrete is taking in compression, and then a little force it can take in tension also, and then steel is taking all the tension. Steel is taking compression also, it is sharing compression, but on tension we are depending on steel only. And there is an important parameter called curvature. Curvature is given by this angle. So the angle the strain diagram is making, that angle we call curvature. And using this section analysis, we can calculate moment capacity at a given strain distribution. We can calculate moment, and we can plot moment versus curvature. So we get a moment curvature relationship. This is very important. This is the basis of all our analysis. So when we plot moment with curvature, initially the section is intact. It is uncracked. So you can see that the slope of the moment curvature diagram. And you may recall that the slope of the moment curvature diagram, what is that representing? That is representing EI. So EI value of a section is given by the slope. So initially the EI value is much higher when the concrete is intact, because then the whole section is effective. and steel, due to its modular ratio, is effective. Its effective area is larger than the actual area. So the moment of inertia is more than the gross moment of inertia. And then the cracking occurs. After cracking, the effective moment of inertia reduces, or the EI value reduces. Then this curve continues like this till yielding. First yield of the steel occurs somewhere here. So when the yield of steel occurs, there is a nonlinearity in the behavior, and then successively other bars go on yielding, and once the yielding is complete, it will become more or less constant. So we get this type of curve. So first yielding is occurring here, but it is not the first yielding which we take. To define yielding, what we do here, we represent this curve by an equivalent bilinear curve. What is this equivalent bilinear curve? It is consisting of two lines. One is this initial line, and this initial line we draw in such a way that it is intersecting at the first yield, where the first steel bar is yielding. At that point, it is intersecting, and slope of this line is EI effective. And you will see that this EI effective is less than the gross EI value. Gross EI value, which we obtain using BD cubed by 12. So if you are obtaining a moment of inertia of a section by using its gross properties, then the corresponding EI value we call EI gross. So, and this is effective EI. This effective EI is less than the gross EI. In case of beam, it is roughly about 30%. And why it is less? Because the concrete cracks, and in the tensile portion below the neutral axis, the concrete cracks. And due to that cracking, the effective moment of inertia of the section reduces. And where these two lines are meeting, this point we define as the notional yield point, phi y. The curvature corresponding to this we define here. So you can see that the yield point is not on the curve. It is only a notional point here. And what is it? It is representing? It is obtained from the intersection of these two lines in bilinear representation. And it is representing the behavior where there is significant yielding. Several bars in our section have yielded. So it is not the point where the full yielding has occurred. It is not the point where the first yielding is occurring. It is somewhere in between. And ratio of these two, the ultimate curvature, when the ultimate curvature will be reached, when either the steel has ruptured, that means the steel reaches its 14.5%, then the steel will rupture. So this is that point. Or if the steel is not rupturing, sometimes concrete gets crushed. So when the concrete is reaching its ultimate strain, or steel is reaching its ultimate strain, that point is represented by phi u. And ratio of this phi u to phi y, that is the ductility of the section ductility or curvature ductility. And you can see the section ductility or curvature ductility depends on material ductility. So that's why material ductility was important. Then what we do, this section analysis, we extend to analysis of the member. And the simplest member is a cantilever. In case of a bridge, the structure can also be represented by a cantilever. So you know, in case of a cantilever, the bending moment diagram, if force is acting at the tip, then the bending moment diagram is linear. And you know, curvature, what is curvature? M upon EI. So this M upon EI is represented by curvature. And if we plot the curvature, it will be like this, that you can obtain from the previous graph. So here, the moment is increasing linearly. So if this moment increases linearly, the curvature will vary like this. So if you plot it here, moment is increasing linearly from top to bottom. So curvature will increase like this. And by integrating this curvature 2 times, you will get the displacement. So curvature is also second derivative of displacement. So d square y by dx square. So if you integrate the curvature 2 times, you will get the displacement, putting suitable boundary conditions. So our actual distribution of the curvature is like this. Up till this point, no yielding has occurred. At this length here, the first yielding will occur, and slowly the yielding will increase, and the nonlinearity of the curvature will go on increasing. What we do for simplifying our calculations, we represent this actual variation of curvature by a simplified variation where there is one linear variation up to phi y, and beyond that up to phi u. So this portion which is outside this triangle, that we represent by a rectangle. So we define a rectangle here, and the height of this rectangle we represent by LP. We call it plastic hinge length. And this dimension on the curvature axis, this is phi u minus phi y. Phi u minus phi y we call plastic curvature. So this is representing, this ordinate is representing plastic curvature, and this is plastic hinge length. Now, I told you that in case of this cantilever, the yielding started somewhere here and it continued till here. And in fact, in the foundation, into the foundation also the yielding occurred. That's why here you can see this LP goes into the foundation also. This is called length of strain penetration, LSP. So the yield strain, the maximum strain will occur here, and that maximum strain will reduce as we go into the foundation, but it will take a certain depth to become zero. So strain will be penetrated into the member which is joining foundation, or maybe a column if this was a beam. So there is a penetration length of a strain which we represent by LSP, and this total length we call plastic hinge length. Now you can see that this plastic hinge length is not obtained by equating the area, because area of the moment curvature diagram, or area of the curvature diagram, that is the first integral, that is giving us slope. But we are not interested in slope, we are interested in displacement. So this LP is obtained empirically from experiments in such a way that by taking the second derivative of, or second integral, double integral of these two, we should get the same displacement at the top. So LP is obtained empirically, and those empirical models, empirical expressions are available in books, so, and papers. So this LP is obtained in such a way that by getting the second integral, double integral of this area, when we integrate this diagram, we should get the same displacement at the tip as obtained experimentally. So that's how this is obtained. Now, using this, we can convert our moment curvature diagram into force versus displacement. The force and moment are related. What is the relationship in case of a cantilever? The relationship is simply in case of force and moment. Moment is F into H. So if I divide moment by H, I will get force. And curvature, by double integral, I can convert this into displacement. So I will get a curve like this. Up to cracking, the stiffness will be higher. After that, it will reduce. So a similar curve. We can represent this also by equivalent bilinear idealization. So when we idealize this by two lines, we will get an intersection here. That is our yield displacement, and this is the ultimate displacement. And ratio of these two, this is the displacement ductility. Most of the times when we say ductility without any prefix of curvature or strain or material or section, then we mean displacement ductility. So structural ductility is represented by displacement ductility, mu delta. That is delta u by delta y. So we can see that the structure or displacement ductility depends on the curvature ductility, and curvature ductility in turn depends on the material ductility. So from material we obtain curvature, and from curvature we obtain displacement ductility. And to represent the displacement, we have a different definition of rotation which you are familiar with. So usually the rotation which you are using is slope of the displacement curve. So if you differentiate displacement, then you get rotation. In this deformed shape, you will see that the rotation is changing. But we define something which we call chord rotation. What is this chord rotation? Chord rotation is defined as the rotation of the chord. So what is chord? If you join the two ends of a member, in case of a cantilever, here we can see. So if you join the tip with the base, then this is the chord. So how much rotation the chord has made, that we represent as the chord rotation. So this rotation is actually representing displacement, because this rotation is nothing but delta by h. So it is representing the displacement only. So it is the displacement which is represented as a ratio, and that's why we call it chord rotation. So whatever values you will find in ASC 41 for the rotation, actually those are in terms of chord rotation. So this definition of the rotation is slightly different than what we use in our conventional analysis. So this you should keep in mind. Then coming to the behavior of an inelastic structure, we have the behavior, a typical behavior of an inelastic structure like this. We represent this by equivalent bilinear. So this is an equivalent bilinear curve. And the most ideal behavior is where we get a flat line like this. But it may not be always flat. Depending on the behavior, it may have a positive slope, it may have a negative slope. When it is having a positive slope, then we call it as strain hardening. When it is having a negative slope, we call it strain softening. So this is the ideal behavior, which we also call elastoplastic or elastic, ideally plastic behavior, where the initial line is representing elastic behavior, and this is representing perfectly plastic. Perfectly plastic means that the deformation goes on increasing under constant force. And usually we use this behavior, idealized behavior, for our calculation, because that simplifies our calculation. So if you have an inelastic structure, you load it. If it was within the elastic limits, the displacement was less than yield displacement, then what will happen? This will follow the same path in loading and unloading. But what happens when it is yielding? Then after yielding, if you start unloading, then the unloading will not be along the same path, but it will be along this line, which is parallel to the initial slope. So you can see the slope of this line is same as this line. And then the unloading will start like this. And when you have removed whole force at this point, still there is some displacement. That displacement we call permanent displacement or plastic displacement. And if I want to reduce the displacement, I have to apply force in the other direction. And then if I start loading, the loading will be again parallel to this. So this behavior we call hysteresis. And when the structure is elastic, then loading and unloading is along the same path. Then whatever work you do while loading the structure, you get the same amount of energy back when you are unloading it. But when it is subjected to this inelastic behavior, then you see that the work done in loading and unloading is different. The energy which you get in unloading is only a fraction of the total work which you have done. And this causes dissipation, or that energy which you have given, that energy has disappeared. You know, energy cannot be destroyed. It can be only changed to some other form. So whatever energy we have provided, mechanical energy to the structure, that gets converted into heat and some other types of energy, but mostly it is heat. And due to that, the energy gets dissipated. And this dissipation of energy is important to us. And under earthquake load, if we have a good ductile structure, for example, steel, we know steel is, if it is designed and detailed properly, then it is very ductile. Then you can see here you are getting almost an ideal behavior like a parallelogram. So this is the ideal behavior. But if you have a RCC, typical RCC structure, then this cyclic load behavior will be something like this. So you can see here, it is dissipating energy in steel, in concrete, and if you take masonry, then you see that this is another behavior. And if you compare these three, steel, masonry, and concrete, what do you see? You can see that the shape of the hysteretic curve is changing. These hysteretic loops are changing. And the area here, you can see that the area of the hysteretic loop is reducing. This phenomena we call pinching. So because of the pinching effect, this area is reducing. And when the area is reducing, the energy dissipated per cycle by our structure, that is also reducing. So although the ductility may be same, but because of this pinching, the energy dissipated will reduce. And in that case, the structure will be able to resist a smaller earthquake, even though the ductility capacity is same. Another thing you notice here, the loading, all the loading and unloading curves, those are parallel. So you can see that these curves are parallel to each other. But when you see here, the loading curves gradually becomes less and less steep, or the stiffness is reducing. So you can see that the stiffness reduces in successive cycles. This is called stiffness degradation. And at the same time, at a given displacement in successive cycles, the strength is reducing. You can see that the strength is reducing. Compare it here. At a given displacement, the strength was more or less same. But here, at the same displacement, you can see that the strength is reducing. Here, you see. And in case of masonry, even more degradation. So you can see that there is a significant degradation of stiffness and strength. So when we are performing our nonlinear analysis, we have to simulate the nonlinear behavior. And in nonlinear behavior, not only the load displacement curve, monotonic load displacement curve, we have to also simulate the hysteretic behavior. So there are two nonlinear analysis methods. One is static method. In a static method, we are considering monotonic behavior of the structure. And there is dynamic method. In dynamic method, we are considering cyclic behavior of the structure. So when we are considering cyclic behavior of the structure in dynamic analysis or nonlinear time history analysis, we can take into account the behavior under cyclic load. So this degradation can be taken into account. But in case of monotonic load, in case of static method and the so-called pushover method, which you might have heard, it is a static method. So there, it is not possible to take the cyclic degradation. So we try to take this partially into account indirectly using what we call backbone curve. So this red curve, which is an envelope of our cyclic behavior, this we use as the monotonic curve. If the structure was tested monotonically without the cyclic behavior, then you were expecting a behavior something like this, which will have slightly higher strength and much large ductility. But because of the cyclic behavior, this curve will reduce in strength and in ductility. So we use this curve, which is obtained from the cyclic behavior. So a generalized model, which is available in ASC 41, some of you might have seen this model. Actually, this is a backbone curve obtained from cyclic testing of members. So based on cyclic testing of members, a generalized curve is obtained, and this curve is defined in terms of these points A, B, C, D, E, and these parameters, small a, small b, and small c. And in ASC 41, first, this table you might have seen where the equivalent flexural rigidity, the effective rigidity, EI, as I said that EI will be less than the gross EI. So in case of beams, it is 0.3 EI. In case of columns, it will vary from 0.3 EI to 0.7 EI depending on the axial force. As the axial force is increasing, the effective rigidity will increase because the cracking will reduce. And when the cracking is reducing, more section is, a larger portion of the section is in compression. In that case, the effective inertia will be more. And if the column axial force is very small, its behavior will be like that of a beam. And similar to that for other members also, the effective rigidity are available in ASC 41. Then this type of tables are given. From this type of tables, you can read A, B, C, and it also gives the values of rotation corresponding to IO, LS, and CP. So you can see here that this CP is corresponding to B, okay, and C is the residual portion. So the this peak value is matching with the CP. So this collapse prevention will occur when our member has ruptured, when the member has fallen. That is collapse. Between collapse and IO, and yield, we have immediate occupancy and life safety. So immediate occupancy is, this is plastic rotation only. So plastic rotation will be 0 at yield, and after that it will increase, and maximum value you will get here is 0.05. So these two are between 0 and this value. So you can see that this is corresponding to IO and this is corresponding to life safety. So life safety and immediate occupancy, these points are between yield and the collapse prevention. Collapse prevention is the maximum value here. So this is the value of B. This is the value of A. So here we have collapse prevention. Somewhere here we have immediate occupancy, and somewhere here we have life safety. Similarly, in case of shear wall also, it's like a cantilever. We have this table available in SC 41, which you have to read. And keep in mind that the flexural ductility also depend on the shear stress, because there is an interaction between the shear force and the moment. So it is also important to estimate the shear stress at the section where our flexural yielding is occurring. I will skip because I'm running out of time. So I will come to this pushover analysis. This is a static method of analysis, nonlinear analysis. It is in fact the simplest method of nonlinear analysis, and that's why it is quite popular. And most of you might have already heard about this term, pushover analysis. So what is this pushover analysis? In pushover analysis, we are pushing our structure under lateral load. And when it is a multi-degree freedom system, a multi-story building like this, then we have several values of load along the height. And this load we can change arbitrarily. And the sum of these load is represented by base shear. So this base shear is representing the total force, total lateral force, which we are applying on our structure. So if I subject it to some lateral load, then I have to divide this base shear. We have to distribute this base shear along the height. How should I distribute? I should distribute it in such a way that this distribution is as close to the actual distribution during earthquake as possible. So we have to estimate somehow the distribution of the lateral load along height during earthquake. That I will get only after analysis. But you know that in case of earthquake, the fundamental mode has the maximum contribution. So we can roughly assume this load to be varying in proportion to the fundamental mode in that direction. So we distribute this base shear and we take an arbitrary value of base shear to start with. We distribute it along the height, and then we analyze this. Now, if I go on increasing this load, the base shear, which is distributed along the height, what do you expect? Each beam and column will undergo moments, and at certain moment, one of the beam or one of the column or any one member or maybe a set of members will yield. Those will reach phi y or theta y. So where it will happen? It will happen at the location where the demand will exceed the capacity first. Okay, so if you have plotted the bending moment diagrams for a frame under lateral load, you will see that the bending moment is maximum in the beam near the joint. Same is with columns. So the yielding will occur somewhere near the joint, but whether it will occur here or here or here, that we do not know, because it will depend upon the ratio of demand to capacity. So what we do, we analyze our structure under certain arbitrary load, but that is distributed as per the first mode shape, the fundamental mode shape. And when we apply that load, then I will get the demand capacity ratio. The demand will come from the analysis, capacity will come from the design. Whatever reinforcement I have provided, that is the capacity. I can calculate the demand capacity ratio, and wherever the demand capacity ratio is maximum, that I will equate to unity, that I will put equal to 1.0. So that will equate the demand with the capacity at the location where the demand is demand to capacity ratio is maximum. So that will give us the location of the first hinge. So initially, when there is no hinge has taken place, the structure is elastic. I am subjecting it to lateral load. So the relationship between load and the displacement will be linear. The slope of this line, this is representing stiffness of this beam. So this is the linear behavior. Usually you are doing it when you are modeling in SAP or ETABS or STAT. You will get this type of behavior. If you go on increasing the base shear, the displacement will also go on increasing in the same proportion. But in real structure, what will happen? Somewhere there will be a hinge. And at what base shear it will occur? That I can get by equating this demand capacity ratio equal to 1. So I will get the corresponding base shear and the corresponding displacement. Now, once this hinge has formed, now my structural configuration has changed. I have got a release here. So I can model this further, and then it will be represented by another line. Okay. The only difference will be that the stiffness of this line will be now smaller than the previous line because a release has occurred. If I go on doing this successively, I can find out another hinge, and the slope, stiffness of my base shear versus delta roof, this will go on reducing. If I go on doing this, finally what will happen? Finally, there is a possibility that this frame becomes a mechanism. So when the number of hinges will exceed the degree of redundancy, degree of indeterminacy in this frame, it will become a mechanism. Then it will collapse. Alternatively, there is another possibility that this building was subjected to gravity load. When we started our lateral load analysis, it was already subjected to gravity load, the dead load and live load. So under that dead load and live load, it will be subjected to P delta effects. And due to P delta effects, its stiffness will become negative and it will become unstable and it will collapse. So if we go on doing this, we will get a curve here. This curve. This curve is very important property of this structure, what we call capacity curve. So this is the capacity curve, and demand is, this capacity curve, we can get something like this. And these circles, these are representing the different conditions where some yielding occurred. And at some condition, some member will cross the IO limit, some member here will cross the life safety, and when one member will cross the CP or the building as a whole will collapse, any of the two conditions, that will cause this CP limit state. So here we will reach the CP limit state. This is our capacity curve, and we convert this capacity curve into capacity spectrum by converting base shear into spectral acceleration and roof displacement into spectral displacement. So capacity curve we convert into spectral displacement using these simple transformations, which you may be familiar. You can also find these in A.K. Chopra's book. Then we have to calculate the equivalent damping. I said that due to hysteresis, there is energy dissipation. That energy dissipation we can represent as equivalent damping. And this equivalent damping is obtained using this formula, 1/2 pi ED over ES naught. So what is ED? ED is the energy dissipated by the structure under this. And ES naught is the energy, strain energy stored under maximum displacement. So if I join the maximum displacement with the origin, area of this triangle is giving me the ES naught, and area of this parallelogram is giving me ED. So using this ED and ES naught, using this formula, I can calculate the equivalent damping. And you know, when the damping of the structure increases, the response spectrum decreases. So in the new code 2016 version, the table has been taken away, but in the earlier version 2002, there was a table given with reduction factor versus the damping ratio. So from there you can get how much reduction will take place in my demand. That is the response spectrum. So I have a capacity spectrum, I have a demand spectrum. The difference is that the demand spectrum is for a given damping. What is given in the code is corresponding to 5% damping. But in my capacity spectrum, the damping goes on increasing because the area of the hysteretic loop goes on increasing as the displacement is increasing. So here the damping is varying, but here the damping is constant. So what I have to do, I have to obtain the intersection of the two iteratively in such a way that at this point, the damping of the demand curve and the capacity curve is equal. So iteratively, I go on reducing this curve and check whether it is intersecting at the same point, which corresponds to the same value of ductility or not. So if it is satisfying the same damping, in the demand curve and the capacity curve, then we can call this as the performance point. And this performance point is representing the displacement which my structure will undergo during earthquake. And now you already know that which point was my IO, which point was LS, which point was CP, and this is my performance level. So in this case, if I take this point was IO, and I am getting my performance beyond this. So my performance point is between IO and LS. LS was here. So this was IO, this was LS. I am getting somewhere between IO and LS. IO has already crossed. That means my performance is worse than IO, but better than LS. So we will call it LS performance level. So from here to here, all this range will qualify as LS. But if I want IO, then I have to modify my structure in such a way that the performance point should come here. So this is the simplest method of performance-based design, which is based upon static analysis. But here we cannot take into account the energy dissipation. Okay, an alternate method for obtaining this performance point is in SC41. There you can get this performance point directly by using this equation. I will skip this because I'm already crossing the time. So I will skip this. I will go to the next method, that is dynamic analysis. So if we have to perform dynamic analysis, then we have to use time histories. And the main problem in dynamic analysis is, one is that it requires huge computation. So even on a large workstation, you have to run for weeks to get the results. Secondly is selection of the time history, because the codes provide response spectra. Codes do not provide time histories. Time histories you have to select, and selecting time histories is a big task. So you have to select time histories in such a way that those are representing the seismotectonic conditions at your site. So those should be representative of magnitude. Those should represent the distance. Those should represent the site conditions. So how deep is the soil deposit? What is the shear wave velocity in top 30 meters vs 30? So all those conditions you have to keep in mind. Then you will select a time history. Then the time history you will get may not actually correspond to the intensity for which you want to design. For example, suppose this was the response spectrum for which I want to design. This is the response spectrum which I got from the time history which recorded I have taken. And this will not match with this. So what I have to do? I have to use a scale factor. So two types of scaling are used. One is what we call frequency domain scaling, where we modify the frequency content. And another is the amplitude or time domain scaling, where we are multiplying the whole time history by a constant factor. So when we are multiplying it a constant factor, that is considered to be more realistic. Ideal situation will be that I get a time history which is representing the same response spectrum which I want to consider at my site, but that is almost impossible to get. So you will get a time history which is having response spectrum nearer. The shape is also closer to my target response spectrum, and then I will use a small scale factor. Scale factor should not be very large. So if the scale factor is very large, then the characteristics of the ground motions will be different than what we are expecting. I will skip this. So when we are selecting the time histories, two things are important. One thing is that the shape of the response spectrum should be as close to my target response spectrum. And second thing is that the waveform. So in case of time histories, not only the shape of the response spectrum, the shape of the waveform is also important. So we have to select this waveform also consistent with the site conditions. So I get this time history, and this time history I can apply at the base of my structure. Now, to help you, two sets of these time histories are available in FEMA P695 document. and it has three sets, I will say. One is the far field record set, which is at a distance more than 10 kilometers from the fault. Then there is a near field record set, which is within 10 kilometers from the fault. And then in near field records, there is a phenomena what we call pulse or flinge. So there are again two sets there, one with pulse and another one without any pulse. So you can download this, and these time histories as well as other time histories are available on several websites. Okay, some of the websites, one website here I have given, this peer website. This is the address of the website. You can select here, and this website also has the facility to input a target response spectrum. So you can input your response spectrum, which corresponding to which you want to select the time history, and then that's time history you can apply at the base of your building, and you can get the response. Okay, so this is the final slide I wanted to show you. This is based upon incremental dynamic analysis. What we do in incremental dynamic analysis, we take a time history and go on increasing the magnitude of or amplitude of the motion. So if I go on increasing the amplitude of the motion, if I go on increasing the scale factor, the response will go on increasing. And if I plot the response may be interstudio drift. I said that interstudio drift is one of the important criteria in our performance-based design. We will get curves like this. So if you are using a large number of time histories, you will get large such curves, and these curves have a lot of dispersion. So you can see that these are varying. So we will obtain the median and the standard deviation. So mean plus sigma, mean minus sigma, or any other percentile in which you are interested. And we have to do statistical analysis. So this is important, that when you are doing time history analysis, one time history is not going to give you the desired solution, or the solution will not be unique. It will vary from time history to time history. So you have to consider the response statistically. So generally, it is now suggested that we should have minimum 11 time histories, and we can take mean of those as our performance. So when you are designing a building using performance-based design, using nonlinear dynamic analysis, time history analysis, minimum 11 time histories you have to take. You should perform analysis for those 11 time histories, and the displacement, mean of the displacements obtained from different time histories, that you should consider as your performance point. So that's what I wanted to discuss. Thank you so much. I do not know whether all of you were able to hear properly or not, but whatever questions you have sent to Professor Matsagar, we will try to take up as much as possible. And I think I will hand over now to ISET. They will take over and have the further announcements. Thank you.
Okay, thank you so much, Professor Singh, for that extremely lucid presentation. Definitely, we have several lessons to learn from it. So there have been several questions asked. We have picked some of them. I also request other audience to write their questions in the chat box. I'm picking from the same chat box some of the pertinent questions. So first question is, which one of the ATC 40 and ASC 41 is an ideal code to get the required supplemental damping for regular or irregular structures? Question asked by Dr. Kalyana Rama.
Okay. So supplemental damping. Let's see the history of evolution. So ATC 40 and FEMA 273, these were the initial documents which were developed for performance-based evaluation of existing structures. Then it was further developed into FEMA 356, then came FEMA 440, and then came ASC 41. So ASC 41 2017 is the latest document. So ATC 40 is one of the initial documents. The advantage of ATC 40 is that it is very lucid. It explains many things which are not there in ATC 40. So when somebody is reading want to study performance-based design, then usually we suggest to start with ATC40 because then it is easier. But as far as the design and use is considered, then we should use the latest document, that is ASC41.
Okay, thank you, sir. So next question is from Dr. Madekar. Base isolation ensures no structural damage. What are the additional benefits of performance-based seismic design of base isolated structures?
Okay. First of all, it's not true that base isolation provides no structural damage. Okay. It depends on us. We can design using base isolation also our structures to get damage or not to get damage. How to estimate whether my structure is, if I put any base isolation below any given structure, doesn't mean that I will get no damage or IO or maybe CP. So to estimate which performance I am going to get, that is given by performance-based design. So performance-based design is the design method. Base isolation is a technique. So base isolation is one of the technique. We can do performance-based design of base isolated buildings. We can do performance-based design of non-base isolated buildings also. So what performance with or without base isolation I am going to get, that can be estimated using performance-based design. Base isolation is a technique. Like other techniques, it can be used to achieve any targeted performance level. But one distinct advantage I should mention here, that I said that there are three parameters which we try to control. One is the plastic deformation of the structure, another is the interstory drift, and another is the roof displacement. So using other designs, I can control with our conventional design by providing more shear walls and frames. I can control interstory drift and plastic deformation. But then the floor acceleration will increase. So if I want to control all the three, and floor acceleration is also one of the design criteria for my structure, then base isolation is the only technique which we can use. Base isolation or maybe supplemental damping to some extent. But it is base isolation which we use for control of floor acceleration. So if we are having uses of our building in terms of a sensitive equipment for which acceleration is to be controlled, then base isolation is the technique.
Yeah, thank you. The next question is how to decide ductility of structure on the basis of performance level. A question asked by Mr. Kailas Bore. How to decide ductility of structure on the basis of performance level.
Okay, so if you see this table, this table provides you the performance level in terms of inelastic rotation. So from here, you know, inelastic rotation. So you have to read the row corresponding to your design, rho minus rho dash by rho balance, whether it is conforming, transverse reinforcement and not, and the shear. Based upon that, you can read the plastic rotation from here corresponding to the targeted performance level. Once you know the plastic rotation, you can calculate the ductility, because the ductility is ultimate rotation divided by yield rotation, and ultimate rotation is yield rotation plus plastic rotation, and plastic rotation is given from here. So you can back calculate from this rotation the ductility.
Thank you, sir. The next question is related to nonlinear time history analysis. If you can still use the performance criteria mentioned in the ASC 4117, asked by Ms. Manisha.
Sorry, I could not get the question. What is
the question? Is if we are using
Ah.
nonlinear time history analysis, can we still use the performance criteria mentioned in ASC 41?
Oh, yes, yes. ASC 41 gives both. ASC 41 does not give much details of time history analysis, that how we have to do time history analysis. It do not provide you the details of hysteresis. It only says that you have to model hysteresis realistically. So, but the performance level, this table is valid for time history analysis as well. So IOLS and CP will be given by these values only, because these values are obtained from cyclic tests on columns and beams. So these are representing behavior under cyclic load, which is close to that under earthquake. or what you will obtain using time history analysis. So this table is valid there as well.
Thank you, sir. There are several questions that are mainly related to the diaphragm action, rigid diaphragm versus flexible diaphragm. So what are the effects of considering the flexibility of the diaphragm and also in the flat slab construction? So these are several questions related to the same kind.
Okay, so these questions are related to modeling. So how we should prepare a model. Okay, so the model of any structure, whether you are doing linear analysis or nonlinear analysis, you are doing static or dynamic analysis, the model should be as realistic as possible. Means it should be able to represent the behavior of the structure realistically during earthquake. So, but at the same time, if we try to make the model more sophisticated to represent the behavior, then the computational effort will increase. So many times we have a trade-off between the two. In which aspect of the behavior I am interested in, that aspect should be modeled realistically. Other aspects which I may not be interested in, sometimes we overlook. Now coming to the specific questions of, let us say, slab, when we have rigid diaphragm action of the slab. In India, we have mostly monolithic slabs. So when we have monolithic slabs with frames and shear walls, in that case, the slab will act as a rigid diaphragm. And this modeling of rigid diaphragm is important, not only in nonlinear analysis, even in linear analysis. So in linear analysis also, this rigid diaphragm should be modeled. Then the second issue is regarding the flat slabs. So if I want to do performance-based design of flat slabs, so similar tables are available in AC41 for flat slabs also. So I can make an equivalent frame model of the flat slab. I have a separate presentation on that. I can share. If somebody is interested, you can write to me on my email. I will share that PPT with you. You can make a nonlinear model of the flat slab, and you can perform a nonlinear static pushover or nonlinear dynamic time history analysis of the flat slab. And you can check the performance of the flat slab also using similar table given in ASC 41.
Yeah. Then there are several questions on when in the future the Indian Standard Code 1893 will be incorporating the provisions related to performance-based design.
I think within a year, we will be able to do that. First draft has been already done. It is being reviewed by the committee. Once that review and successive revisions are over, it will be put for wide circulation. So I feel 1 year to 18 months, it should be there.
Okay. So there is a question related to slide number 34.
34. Yeah.
The question is, how much is the plastic hinge length or height in terms of shear wall length or horizontal dimension in maximum inelastic curvature in a shear wall?
Okay. So as I said, that the plastic hinge length is a notional concept. It depends on the yielding, but it is not the length in which the steel is yielding. It is obtained experimentally from equating the displacement. For example, here, what we will like that experimentally, what was the displacement at the top here? Analytically, by considering that plastic hinge length, we should get the same displacement. By equating the two, we get the plastic hinge length, and from using regression, several models are available. So there are some models available in the book, Displacement Based Design by Priestley et al. So you can see from that book, which I have given the reference here. So they have models for columns and shear walls. Roughly, you can take plastic hinge length as LW by 2. So this is the length of the wall, LW. Half of that you can consider as the plastic hinge length, roughly.
Okay, thank you, sir. The next question is related to the capacity spectrum method. In obtaining the performance point, how do we obtain demand spectrum since the graph is between acceleration and time period?
Okay. Yeah, I skipped that part was there. So actually, our capacity curve is in terms of base shear and roof displacement, and the demand curve is in terms of SA and T, spectral acceleration versus period. So here we have there we have SA and T. How to compare them? That was the difficulty. So what we do, we represent both of these curves, demand and capacity, in a common format, a common axis system by mapping. And what is that common system? That common system is SA versus SD. We also call it ADRS format, acceleration, displacement, response spectrum. So there is a response spectrum which relates SA versus SD. So you know there is a relationship between SA and SD. SA is omega square into SD, and omega is 2 pi by T. So SA is 4 pi square by T square into SD. So using this relationship, we can convert SA and T in terms of SA and SD. So at any given value of T, I read the value of SA from my conventional response spectrum, and then that SA dividing by omega square, and that is multiplying by T square by 4 pi square, I can convert that into SD. And then both of these curves I can plot in terms of SA versus SD. So demand curve is also in terms of SA and SD. Sorry, this is the demand curve, which is also in SA versus SD. The capacity curve is also in terms of SA versus SD. For converting the capacity curve, we use this relationship, which I have given here. So from the roof displacement, I can get SD. From the base shear, I can get SA. So when both are represented in the same format, then I can compare this. I hope he has got some idea. Actual, it will be clear if we are having an illustration and doing ourselves, but some idea.
Yes, there was one suggestion if some example could be taken, but I'm sure in this given time it is not possible.
I mean, yes.
The next question is, while developing fragility curves, what shall be the effect of eccentricities on the different performance levels, mainly for asymmetric buildings?
So when the building is asymmetric, then it will have additional deformations because of the torsional response. So we will have translation as well as torsion, and due to that, some of the columns which are in the extreme frame, those will be subjected to larger displacements and larger inelastic deformations, and there the performance levels will be reached earlier. So in other words, the performance level will be achieved at a lower intensity of earthquake. So in other words, the performance will deteriorate, performance will reduce.
Thank you, sir. The next question is, the ASC tables provide acceptance criteria of members. How can we extend that to structures? The critical number is in life safety level, but many are in the life safety level or vice versa. So how to define the building's performance? Is there any general recommendation?
Okay. The question here is that if a member collapses, can we call collapse of the building? It's a tricky question, difficult question to answer. If you look from one way, you will say no. If you are looking from a structural engineer's point of view, how can we say that if one member has collapsed, then the building has collapsed? If you look from the occupant's point of view, can you accept one member collapsing in your structure? So when you are designing a building, you should ensure that none of the members should cross collapse prevention. So collapse prevention of first member, as soon as your first member is crossing collapse prevention, that is collapse prevention limit state. So usually that is the definition for the whole structure. But there is an alternate way of looking at it also. That is in terms of interstory drift. So the global collapse of the structure is controlled by interstory drift. But such limits of performance levels in terms of IOLS and CP are not available in terms of interstory drift. Some values are available for collapse prevention, but that also varies. So it will vary from building to building. So in case of interstory drift, it is difficult to define. So as such, many people have tried to define some acceptance criteria, some performance levels based upon the global parameters, but those are difficult to define. No success so far. So mostly in ASC 41, we depend on the performance of individual components. And we like to ensure that none of our members should exceed the targeted performance. That's what we ensure.
So there are several questions yet to be asked, but because of time constraints, we need to conclude now. So before we conclude, I would request you to give some concluding remarks, and then Professor Ravi Chakka can take over. Thank you so much.
I give concluding remarks.
Yes,
okay.
sir.
Okay. So I'm very thankful to ISET for initiating this series. This series will be very important. I can see that. And the advanced topics are being covered, which our audience may be interested in. So let's appreciate, applaud for ISET for taking up this initiative. Then all the participants, I'm really thankful for registering in such large number. That shows that there is interest in our country on learning these topics. And we will have some lectures in future also. And hopefully we will have the same type of interest there. And if we are getting interest from the audience, we can take up other topics also. If we find this suitable later on, if you want to see a demonstrative or illustrative example on performance-based design or performance evaluation of an existing structure or already designed structure, we can take up that. So you can send your suggestions and your preferences for the future lectures. We can try to arrange that. Okay, I have already got one request for arranging one lecture on non-structural performance, because today we mostly covered structural performance. So we can think of non-structural performance also, how to estimate and ensure performance of non-structural components. So thank you very much again. And now I hand over to ISET to take up further proceedings.